Welcome to another session of this topic of calculus. Today we continue on vector spaces, and this is the third part of this series. So here, what we'll do is we'll look at the specific topic of linear functional. We'll also look at what we call coordinate functional. We'll look at what an isomorphism is. Also proceed and maybe do a quick revision on things. But before we do that, we'll look at what an eigenvalue, as associated to transformations or functions. And then we'll begin stepwise look at what a bijection is, which derives from the two concepts of injection or injectivity and surjectivity or surjection, and then build all the way up to what an isomorphism is, so isomorphic correspondence or relationships. So it's going to be an interesting set of topics that we'll look at. We'll just go slowly, methodically, try to understand them. And if you have a question on your end, please feel free to reach out. We are open to criticisms. We are open to, suggestions to keep this space growing. Thank you. So let's begin by looking at the concept of what a linear functional is. So if we have a linear functional, f, that is subject to a collection of ordered lists of n real numbers, in other words, on R to the n, this is considered to be a linear mapping from the R to the n space, in other words, a space where you have ordered lists of n real numbers, to a real number, and that's R to the 1. And this must be expressed by a 1 by n matrix, right? So that when you have this 1 by n matrix corresponding to this linear function of f, and you multiply it to a vector of n, or to a tuple, n tuple, then you get one real number. So what that means is that this is that the n tuple b, which is an element in R to the n, which is a skeleton of f, is viewed as a matrix of one row and n columns, right? So one row and n columns. So let's begin back from what we saw as a transformation from R to the n, in other words, an n tuple to an n tuple to an m tuple. So if we have a linear mapping Y, that's an m tuple that is transformed from an n tuple, that is a vector x consisting of n elements. So you have something like this. So you have these x elements, and then correspondingly we have these vectors of m items. So we have across we have n items, and going down we have m items. So the T here is a representation of a matrix. So we have a two-dimensional matrix that has m rows and n columns, right? And an easier way is to take each vector here as beta 1, beta 2 up to bn, beta n, and in each beta element you have m items going down. So this is considered to be a linear function, a linear functional f, now, as opposed to T, which is an n to m transformation, consists of a y, which is a one element item transformed from x, which is still an n element item, and f here, instead of t, f here has to be a 1 by n matrix. In other words, how we would express it, it's y is equals to b1 times x1 plus b2 times x2 all the way up to bn times xn. And this all adds up into one real number, right? So F can be considered as a matrix, or I mean, I don't need to include this comma, but just a 1 by n matrix. So that's what you could actually look at a linear functional F as opposed to the T transformation that transforms, or a linear transformation that transforms an n, r to the n to r to the m. Okay. So we have a very interesting concept here. So if we have a vector space V, which is equal to r to the capital I, where capital I can be an integer I, the ith coordinate functional, this is a special function, pi I, is simply evaluation at I, so that if you have pi I of a collection of functional or functions f, then that is just going to be the function at I. So let's take it a little bit. This might be a little bit abstract at this point. Now these functionals are obviously linear, such that if you have a pi I of a real number s times the functional g, or function g, plus a real number t times the function g, this is equivalent to just, based on this expression, as s pi I f plus t pi I g. So this is linear for all i's. So an example that really illustrates the point is that if we have V, which is equals the vector space which corresponds to an n tuple, then pi j is the mapping of this vector x consisting of these n tuples that extracts the xj term. I think that makes it clear. So that if we have pi j of x, if we have pi xj being equal to this linear combination of this x of the n tuple here, b, so for some n tuple b, which is just a combination of real numbers, then we can obviously see that b is just a 0 and 1 at the jth term, right? And this obviously it's also something that we can interpolate and say, okay, if we have a linearity property, a transformation of this linear combination, this is equivalent to obviously a linear combination of the transformation T. So this property here shows that T and the inverse of T both transform one space to the other. So they both carry subspaces into subspaces. So the important thing here is we have seen what a coordinate functional is, and that is a functional that extracts the ith term in this situation where we have a coordinate functional at the jth term that extracts the jth item. And then we've also seen that if you have a linear combination of the input n tuple with another n tuple b, then the b for linear functional, this coordinate functional is 0, 0 and 1 at the specific index item that you're focusing on. We've also seen that if you have this linearity property where a transformation of a combination of a linear combination being equivalent to a linear combination of the transformation of independent vectors. This shows that both the linear transformation, the transform T and its inverse both do carry subspaces into subspaces. So we have a very interesting theorem here that if we have a transformation T from a vector space V to a vector space W that is linear, then the T image, in other words, the transformation that we obtain on a linear span, in other words, a linear combination of any subset, that's a collection of vectors that make up A, that are elements of the vector space V, that the image of that linear span in itself is a linear span of the T transformation, the T image of the primary collection of vectors A, and that we can see from this here, so that if we have the transformation of a linear combination, or this a linear span of A, by the property of linearity of T, we can pull the L out and T goes in. So in other words, the T image of this linear span here in itself is a linear span of the transformation, the T transformation, or the T image of A. So this is obvious. Now we can say in particular, if A is a subspace, then so is the transformation on A. Furthermore, if Y is a subspace of W, then the inverse transformation of Y is a subspace of V. Okay. One other thing that we would like to say is that the subspace, the inverse transformation of 0, if that be equal to alpha, which is an element of V, then we can say that the T transformation of alpha is 0. And alpha is definitely called the null space or the kernel of T, and it's designated as NT. It's also worth mentioning that the range of images that can be obtained from T is the subspace TV of W, and this is designated as RT, or this are written in a fancy way, and T. The important thing to note is that this is a sub-theorem, that the linear mapping T is injective if and only if the null space is 0. In other words, if alpha here is 0. And we're going to talk about what injectivity means, but for now, if T that is linear be injective, in other words, if it has a 1-to-1 correspondence between the input and the output, then alpha, or the null space, must be 0. One other notable thing to mention is that a linear map from the V space, a linear map T from the V vector space to W vector space, which is bijective, is called an isomorphism. And we'll talk in detail about what a bijective mapping is, or function is. Thus, two vector spaces V and W are isomorphic if and only if there exists an isomorphism between them. In other words, we have a transformation that is bijective between them. When a linear transformation is from V to itself, such as if you have T or that the mapping T on a vector alpha that amounts to a multiplication of a real number and the same vector, where x is any real number. In that case, alpha is an eigenvector, or sometimes we call it a proper vector or a characteristic vector. And then x there, that real number, is the eigenvalue. And we know this for those of us who have looked at linear algebra. Matrices, some matrices tend to have eigenvectors and eigenvalues or eigenvalues. This is the same concept where if you have a transformation that converts a vector, a specific vector, to itself, and that vector is considered to be an eigenvector, and the real number, there's a constant that is multiplied by that vector, is an eigenvalue. This is a very important concept also in engineering, but we won't really cover that. So I would like us to maybe step back a little bit and look at the concepts of injectivity, surjectivity, bijectivity, and then isomorphism, just to illustrate, make the what we've talked about here clear, because we say that if a linear mapping from the T space, of a linear mapping T from the V vector space to a W vector space, if that linear mapping is bijective, then we consider that mapping to be an isomorphism, and V and W are considered isomorphic because there is isomorphism between those two vector spaces. To go through a revision on some of the concepts that we covered. So we looked at the types of mappings, and let me use just very elementary terminology. And by mapping, let me use the word function here. So an injective function or injective functions are called one-to-one functions. And they do map distinct elements to distinct elements. That means that if you do have two real numbers, x and y, and they are not equal, then the result of us feeding those real numbers into a specific function f that is injective would result to fx and fy, and fx and fy won't be equal if x and y are not equal. So an injective function means there's just an arrow that points from input to output, and the arrows don't cross each other, or two arrows don't lead into one arrow in the image space. There's one to one. An example is fx equals to x is an injective function, since if you have two real numbers, x1 and x2, that are not equal, then definitely fx1 and fx2 will never be equal. Now, fx equals to x squared is not an injective function because two different real numbers, -2 and +2, all amount to 4, and so we see here -2 and +2 are not equal, but f of -2 and f of +2 are equal. So this is not an injective function. Then what is surjective functions? Surjective functions are also called an onto functions, and this means that for all y being members of a vector space B, or a codomain or a space B, there is an x in the A domain such that fx equals to y. In other words, for any output or for any item in the codomain, there is a corresponding item in the domain space. So a function such as f that transforms a real number to a real number of fx equals to 2x is surjective, because you could always find a value in the x domain that gives you a value in the 2x domain. However, a function that transforms a natural number to a natural number such that fx equals to 2x is not surjective, since for an output, in other words, a y equals to 3 or 2x equals to 3, there is no x in the natural number domain that would yield 3 in the codomain. So this second relationship is not surjective. Now, an important concept of bijectivity or a bijective function is one that is both injective, that's a one-to-one forward correspondence, but also a backward correspondence, that is surjectivity. So a bijective function is one that is both injective and surjective. That is for a function f that transforms items in the space A to space B. There is an inverse function g that transforms all items from B to A, so that the composition g f of A is an A to A is the identity function on A, while fg of B to B is an identity function on B, right? That is, G is an inverse function of F, and F is an inverse function of G. Two vector spaces V and W are isomorphic if there is a bijection T from the V space to W space, which preserves addition and scalar multiplication. And that is for all vectors of U and V in V, and also all scalars in the F space, all scalars C in the F space. And this is just a quick illustration or where you have addition of two vectors, small u and v. That transformation that is isomorphic corresponds with the sum of the two independent transformations of on u and v. But also if you have a multiplication of c and u, that's the same as c times the transformation of the independent, the vector u. The correspondence T is an isomorphism of the vector space if this bijectivity holds, and we've already looked at that previously. Then if T is a mapping from V space vector space to W vector space, is an isomorphism. If that holds, we can express it in this format where we have an arrow and then this sign on top. Or if T is not specifically mentioned, then we could just say V arrow and then the same expression above into W. Okay, so that's a quick run through that. Quick theorems that don't really need us to dwell so much on is that if the transformation T from, or mapping T from V to W vector spaces is an isomorphism, then the inverse T to the power -1 is also an isomorphism from W's vector space to the V vector space. And then if S is an isomorphism from the V vector space to W vector space, and T is another isomorphism from the W vector space to the X vector space, if both these S and T are isomorphisms, and then the composition T and S is also an isomorphism from the V vector space to the X vector space. Another theorem, if T again is an isomorphism from V vector space to W vector space, then T carries linearly independent sets to linearly independent sets, spanning sets to spanning sets, and bases to bases. And we'll talk a little bit about what bases are. Now, one of the most important, uses of bases is for a vector space V is to be able to impose coordinates on that vector space. And we're going to look at how that, builds up. That means that for any vector in the V vector space, it happens to be a linear combination of the basis vectors. And for example, for the Euclidean vector space, or the three-dimensional vector space, the basis vectors are in the x direction 1, 0, 0. In the y direction is 0, 1, 0. In the z direction is 0, 0, 1. In other words, and so you can build any vector in the Euclidean space, the three-dimensional Euclidean space, using these three basis vectors. So, so if you have, for example, the n-dimensional vector space, you see that it's the same as having a linear combination of the vector spaces, the basis vector spaces, b1, b2, all the way up to bn, with these constants or combination constants or coefficients v1, v2, v3, all the way up to vn. Up to vn are used as coordinates for the vector v with respect to the basis beta, right? And this is how we would express it. The important thing to know is if a function extracts these coefficients from the vector v, and that is denoted as phi beta, then the correspondence from the vector to the coefficients is an isomorphism that extracts a vector from vector space v into an n-tuple that we see here. Okay, so that really pretty much covers everything we wanted to look at this time around. We've looked at linear functional, we've looked at coordinate functional, we've looked at what an isomorphism is, and we say that if a linear transformation is injective and also surjective, then that transformation or linear mapping is an isomorphism. We've also kind of looked at the transformation where you have a transformation that transforms a vector to itself. We say that is an eigen vector if the vector is transformed to itself, but also if there's a constant that results when that transformation of mapping happens, we call that constant an eigenvalue. Then we've gone and looked at the concept of injective functions. We looked at the concept of surjective functions. We looked at bijective functions as being both injective and surjective, and we looked at the concept of isomorphic functions or isomorphic mapping, and then we also look at the concept of basis vectors. And so I hope you learned quite a bit. Until next time, it was really nice hanging out with you. Bye-bye.